In this video, we'll learn a technique called implicit differentiation, which is really just an application of the chain rule. Sometimes it is not possible to write y as an explicit function of x. Consider the ellipse with the equation x squared plus 3y squared equals 3. The ellipse is not the graph of a function. For given x, we have two different y values. That is to say that it does not pass the vertical line test. If you draw a vertical line, it will intersect the graph twice. However, it is still possible to find a formula that will compute the derivative dy dx at any given point on the ellipse. This method is known as the implicit differentiation method, or simply implicit differentiation. Step 1. Write out the relationship between x and y as an equation. Step 2. Differentiate both sides with respect to x. Treat y as an unknown function of x. So for step 3, whenever you encounter a y and you want to differentiate it, write dy dx or y prime. Step 4. Solve for dy dx. Let's consider our ellipse again. X squared plus 3y squared equals 3. Let's use implicit differentiation to find a formula for dy dx at an arbitrary point x comma y. So we simply write down the equation x squared plus 3y squared equals 3. And then we differentiate both sides of this equation with respect to x. On the left side, you can see that we have the derivative of a sum, so you can differentiate term by term. And you'll have the derivative with respect to x of x squared plus the derivative with respect to x of 3y squared. On the right, we have the derivative of a constant, so that will just be 0. On the left, we have two derivatives. So the first one, the derivative with respect to x of x squared, we can use the power rule. That's 2x. Well, what about this one, the derivative of 3y squared? Well, we treat y as an unknown function of x. Y is equal to y at x. But we don't actually know what that is. But we think of it as being a function of x. So when we differentiate y with respect to x, we use the chain rule. So for example, if you want to differentiate with respect to x y squared, then you have the derivative of something squared. So you have an inside function, which is y. The outside function is something squared. So the derivative of something squared is 2 times that thing times the derivative of whatever goes inside that function. So right there and right there. Those are our inside functions. The inside function goes here. But it also goes here. So the question is, what is the inside function? The inside function is y. We don't actually know what y is as a function of x, but we know it is a function. So we just put y inside. So the derivative of y squared with respect to x is 2 times y times the derivative with respect to x of y. Notice that we're just applying the power rule to y squared. That becomes 2y. But then we just multiply by the derivative of the unknown function, dy dx. So if we go back to our equation, where we're differentiating both sides, we want to differentiate 3y squared. So we can take the constant out, and then it's 3 times the derivative with respect to x of y squared. And we know what that is now. The derivative of y squared with respect to x, that's what we determined over here. So this quantity is 2y times the derivative of y with respect to x. So let's put all of this together now. So we have that 2x plus 3 times 2 is 6, y times dy dx is equal to 0. Now the final step is to solve for the unknown quantity. So we're going to solve for dy dx. We can subtract 2x from both sides, and then we have 6y dy dx is equal to negative 2x. And then we can divide by 6y. So we'll end up with dy dx is equal to negative 2x over 6y. And of course, you can simplify that by reducing the fraction, and that will give you that dy dx is equal to the opposite of x over 3y. And this is the derivative of y with respect to x at any given point x comma y. Notice that the derivative includes x's and y's, so it depends on what point you're looking at, and that makes sense because you're trying to find a formula for the slope of the tangent line at a specific point on the curve, so it makes sense that you need to know both the x and y coordinates. In fact, let's do that. Let's find an equation for the tangent line to this ellipse at a given point. So from the previous slide, we know that at x comma y, the derivative dy dx is equal to minus x over 3y. So that tells us that at square root of 3 over 2 comma square root of 1 half, we have that dy dx is equal to the opposite of the x value divided by 3 times the y value. Now this gives us the square root of 3 over 3 with a minus sign in front, because this square root of 1 half cancels with the square root of 1 half. So our slope of our tangent line is the opposite of the square root of 3 over 3. So this is the slope of the tangent line at the given point, which is the square root of 3 over 2, comma, the square root of 1 half. Once we have the slope, we can find the equation for the line because we were given a point already. The point was given to us. And now at that point, we also know the slope of the tangent line. So putting all of this together, we have that the equation, or an equation, is y minus the y value is equal to the slope times x minus the x value. And this is the equation of the tangent line at that point. The curve having equation x cubed plus y cubed equals 3xy is known as the Folium of Descartes. The Folium of Descartes is not the graph of a function. If we draw a vertical line in certain places, it will intersect not once, not twice, but actually 3 times. Remember that in order to be a function, any vertical line must intersect the graph at most once. But here we've drawn a vertical line that intersects 3 times. So we know that this is not the graph of a function because if we specify this x value, we don't know which y value it corresponds to. Even so, we can see that at all of these points, it is possible to draw a tangent line. The slope will be different for each tangent line depending on which point you're picking. So the question becomes, how do we determine the slope of a tangent line? Well, of course, you need to specify which point you're looking at, because each point will give you a different slope. But how do we find that formula that depends on the point? Well, we start with our equation, and we use implicit differentiation. So here's the equation for our Folium of Descartes, x cubed plus y cubed equals 3xy. So we start by writing that down. X cubed plus y cubed is equal to 3xy. And now we differentiate both sides with respect to x. Again, on the left, we have a sum, so we can differentiate each of these individually. And on the right, we're going to have a product. So this is 3 times the derivative with respect to x of x times y. If we just use the constant multiple rule to take out that constant, we don't have to take it out. We're just taking it out just to make our computations a little bit easier. So let's start with the leftmost term. The derivative with respect to x of x cubed, we simply apply the power rule, 3x squared, plus, and now we need to apply the chain rule. We have the derivative with respect to x of a function raised to the 3 power, something cubed. So the first thing we do is we use the power rule on that cubic function. So this will be 3 times that function squared, but then we have to multiply by the derivative of that function. Now, we don't know what the derivative of y is with respect to x. In fact, that's what we're trying to figure out. So we just write dy dx. But dy dx is just the derivative of our inside function. The inside function is y. So we just compute the derivative of y with respect to x. And again, since we don't know what the derivative of y is with respect to x, we just write dy dx. So that's the left side. On the right side, we're going to use the product rule. So we start with the derivative of the first function. Let's write it all out. The derivative of the first function times the second plus the first function times the derivative with respect to x of the second function. Our first derivative here, the derivative of x with respect to x, that's just 1. And our second derivative, the derivative with respect to x of y, that's something we don't know. So whenever we encounter it, we just write dy dx. So putting all of this together, we have that 3x squared plus 3y squared times dy dx is equal to 3 times y times 1 plus x times dy dx. And now we solve for the unknown quantity, which is dy dx. Solve for dy dx. Just treat it like an unknown. So 3x squared plus 3y squared dy dx is equal to 3y plus 3x dy dx. And again, we just want to group everything together that has a dy dx. So let's subtract those terms to the other side. So we'll have 3y squared dy dx. Let's get them all together. So we're going to subtract 3x dy dx. And this is going to be equal to 3y, and then I'm going to subtract the 3x squared. Let me just highlight those, and let me just comment that this 3x here is the same as that 3x there, and this 3x squared is this 3x squared here. Okay, so now the next thing to do is just solve for dy dx, but first we factor it out. So we'll have dy dx times 3y squared minus 3x, and that's equal to 3y minus 3x squared. And now we just simply divide by this quantity 3y squared minus 3x, and that will give us our formula. So we'll have the dy dx is equal to 3y minus 3x squared, and then we divide by 3y squared minus 3x. And this expression is the formula for our slope of our tangent line at a given x comma y. So we need to know what the coordinates of the point are. If you know the coordinates x comma y, then you can just plug in x and y into this formula and it will give you the slope of the tangent line at that point. The curve having equation y equals sine of xy plus 3 does not represent a function of x. As you can see, if you draw a vertical line in certain places, it will intersect the curve in more than one point, and therefore it's not the graph of a function. However, we can still find the equation of a tangent line at a given point using implicit differentiation to determine the slope. So let's find a general formula for the slope of a tangent line at a point x comma y for this equation. So we have that y is equal to sine of x times y plus 3. So again, we differentiate both sides with respect to x. On the left, there's not really much to do for this example. It's just dy dx. On the right, we have the derivative with respect to x of sine of x times y plus the derivative with respect to x of 3. The derivative of a constant is 0. And here we have sine of xy. So this is a composition. So we're going to have to use the chain rule. But notice that inside of our sine, we have an x times y, which is a product. So we have a little product there. So that means we're going to have to use the chain rule and also the product rule. So let's just go ahead and do that. So we have the derivative of y with respect to x is equal to the derivative of sine. Well, the derivative of sine is cosine of a thing times the derivative of whatever's inside of cosine, whatever that thing is. And in this case, that inside thing is this x times y. And then to this we add 0, but we don't actually have to write that down, so you don't need to worry about that. But what about this term right here? This is a product, so we need to use the product rule. So we have that dy dx is equal to cosine of x times y times, and now it's the derivative with respect to x of x, the derivative of the first, times the second, plus the first times the derivative of the second. Our first derivative here is the derivative of x with respect to x, which is 1. And our second derivative is the derivative of y with respect to x. Well, we don't know what that is, so we just write dy dx. In fact, that's the thing that we're trying to identify. So what we want to do is we want to identify this dy dx. So we're going to solve for that. Let's just rewrite this all in one line. So dy dx is equal to cosine of x times y times 1 times y is y plus x times dy dx. So this is the equation that we want to solve for dy dx. Solve for the unknown quantity. And we're going to end up with a formula that involves x's and y's, and that's okay because you have to specify the point, and once you specify the point on the curve, then you can determine what the slope of the tangent line is. So let's just go ahead and do this. So dy dx is equal to, let's distribute this cosine of x times y. So cosine x times y times y plus cosine x times y times x dy dx. We want to get all of these dy dx's on the same side. So we'll have dy dx minus cosine of xy times x dy dx. And this will be equal to cosine of xy times y. Now we just factor out that dy dx there. dy dx, and this will be 1 minus cosine of xy times x is equal to cosine x times y times y. As a matter of convention, it's usually the case that you want to take this x and put it in the front. So let's just take that x and put it in the front. We'll take this y and we'll put that in the front of this cosine. So we'll have dy dx times 1 minus x times cosine xy is equal to y times cosine of xy. And again, the thing that we're trying to solve for is this dy dx, so we just divide by everything else. And so we'll have dy dx is equal to y times cosine of xy divided by 1 minus x times cosine of xy. And this is our formula. It depends on x and y because you need to specify the x-coordinate and y-coordinate of the point on the graph. And once you specify that, then you can determine the slope of the tangent line there. In fact, let's do that for a specific point. Let's write down the formula that we've just established for the derivative. So this will be y cosine xy and divided by 1 minus x cosine xy. So we want to use this formula. This is the formula for the slope. So this is the slope of the tangent line at the point x comma y. So now we're given a specific point, pi comma 3. Now you should just double check and make sure that this point actually is on the graph, and it is because when x is pi and y is 3, sine of 3 pi will be 0, and then we'll just have that y is equal to 3. So yes, this is a point on the graph, and now in order to determine the slope of the tangent line at this point, we just take this point with coordinates x equals pi and y equals 3 and plug that into this formula here. So when x comma y is equal to pi comma 3, then dy dx is equal to y is 3 times cosine of x is pi times 3 for y divided by 1 minus x is pi times cosine, and again this is x times y, so that's pi times 3. Okay, now what is cosine of 3 pi? That's going to be using periodicity. That's the same as cosine of pi. So this is going to be equal to -1, and this one's going to be equal to -1 as well. So cosine of pi times 3 is equal to -1. And that means that dy dx is 3 times -1 over 1 minus pi times -1, which is -3 over 1 plus pi. So this is the slope of the tangent line at this point. So that means if we want to find the equation of the tangent line, and we do, then the equation is y minus the y value is equal to the slope times x minus the x value. And this is our equation for the tangent line in point-slope form. Let's do another example. The curve having equation x to the 4 plus y to the 4 equals 4 times xy, again, does not represent a function of x. Once again, it does not pass the vertical line test. If you draw a vertical line, it may intersect more than once. So we can't solve for y and get an explicit formula for y. Instead, we have to use this implicit form, and that's why it's called implicit differentiation. So let's just go ahead and find a formula for dy dx at an arbitrary point x comma y for this equation. So we just do it the same way. We have x to the 4th plus y to the 4th is equal to 4xy. And we differentiate both sides with respect to x, And again, we just treat y as an unknown function of x. So we have on the left here, we have the derivative as sum, so we can differentiate each one of these terms individually. So the derivative of x to the 4 with respect to x is 4x cubed, using the power rule. And then when you get to this y to the 4, you use the power rule again because you're using the chain rule. So the derivative of y to the 4th is 4y cubed. But then you just have to multiply by dy dx. Now this will be equal to the derivative of a product. Now let's treat 4x like one function. So it'll be the derivative with respect to x of the first function, 4x, times y, plus 4x times the derivative with respect to x of y. Now the derivative of 4x with respect to x is 4, and the derivative of y with respect to x, well, we don't know, so we just write dy dx. So what do we have here? We have 4x cubed plus 4y cubed dy dx is equal to 4y plus 4x dy dx. And again, the thing we want to solve for is dy dx. So we can subtract this term over to the other side. So we'll have 4y cubed dy dx minus 4x dy dx, and this will be equal to 4y minus 4x cubed. So once again, we're taking this 4x dy dx and we subtract that over here, and then we take this 4x cubed and we subtract that over here, just so we know where everything is. And now we factor out the dy dx. dy dx, we're just factoring this dy dx. So then we'll have 4y cubed minus 4x is equal to 4y minus 4x cubed. And then we just divide by this term, and we'll have our formula. dy dx is equal to 4y minus 4x cubed divided by 4y cubed minus 4x. In fact, you can reduce this because there's a factor of 4 in the numerator and in the denominator. So if you wanted, you could just go ahead and reduce this. Get dy dx is equal to y minus x cubed divided by y cubed minus x. And that's our final answer. Now this gives you the slope of a tangent line at a specified point x comma y. So if you know that point x comma y, then you can determine the slope of the tangent line. Here's another example, a double spiral, having equation tangent x squared plus y squared equals y over x. Now this does not represent a function because it certainly does not pass the vertical line test. If we draw a vertical line passing through here, you can see that, well, in fact, it will intersect the curve infinitely often. But we can still find the slope of a tangent line at a specified point. Let's go ahead and do that. So in this case, the point we're interested in is the point with coordinates square root of pi, comma 0. That's just to make the computations a little bit easier in the end. But you can check that, yes, this does, in fact, satisfy the equation. So this is a point on the line. You just, y is 0, so the right side is 0. The left side is tangent of pi, which is also 0. Okay, so we're just going to do this in the usual way. We have the tangent of x squared plus y squared is equal to y over x, and we're just going to differentiate both sides with respect to x. Computationally speaking, it would probably be easier to multiply x to the other side and then use the product rule, but we can also just use the quotient rule. So on the left, we'll have the derivative of tangent, which is secant quantity squared. So the derivative of tangent is secant squared, and then we just take the inside function and you put that here. But then of course you have to multiply by the derivative with respect to x of whatever's inside there, which is x squared plus y squared. And this will equal, using the quotient rule, the derivative of the top times the bottom minus the top times the derivative of the bottom. And all of this is divided by the bottom squared. Okay, so let's just comment on what we did. We started with the derivative tangent of a thing. So that's going to be secant squared of that thing times the derivative of whatever that thing is. So now, this term here, you don't have to do anything else with the secant squared term, but you do have to differentiate this term right here. And we can do that term by term. The derivative of x squared is 2x, plus the derivative of y squared is 2y times dy dx. This is y to a power, y squared. So if you're differentiating something to a power, you use the power rule. So the derivative of something squared is 2 times that thing. But we don't know what y is as a function of x. So you have to multiply by dy dx. That's the derivative of the inside. So the inside function is y. The outside function is the square function. So that's why when you differentiate it, you end up with 2 times that thing. 2 times the inside function. But then you have to multiply by the derivative of the inside function. And we don't know what the derivative of the inside function is. That's really what we're trying to determine. So you just write down dy dx. Here there's another dy dx over here. We also have this d by dx of x, but of course that's just 1. So if we put all this together, we'll have the secant of x squared plus y squared, quantity squared, times 2x plus 2y dy dx is equal to, so let's write this as x times dy dx minus y. So just keep in mind that I moved this x to the front here. And then we're going to divide all of this by x squared. So 2 things to keep in mind. So this x I just moved to the front. And the other thing to keep in mind is that this derivative of x with respect to x is 1. So that we don't actually see that here, but it's y times 1. Okay, so what we could do at this point is we could solve for dy dx. So there's a dy dx here and a dy dx here. We could solve for dy dx and get a formula for the slope of the tangent line at an arbitrary point x comma y. However, we don't actually need to do that because we're only looking at this one specific point. So all we have to do is look at what's going on at the point square root of pi comma 0. And this is going to make our life a lot easier because now you just plug in x equals the square root of pi and y equals 0. And then you solve for dy dx. So if we do that, we'll have the secant of x squared, so the square root of pi squared, plus 0 squared, and all of this quantity is squared, times 2 times the square root of pi, plus 2 times y is 0, times dy dx. And this is equal to x, which is the square root of pi, times dy dx, minus y, which is 0, divided by the square root of pi quantity squared. And notice how nice this is going to simplify. Here we have 2 times 0 times dy dx, so that gets rid of one of the dy dx's. Here we have a 0 squared, but more importantly, here we have secant of pi. Secant of pi is 1 over cosine of pi, so that's just going to be negative 1. So we're going to end up with negative 1 squared times 2 square roots of pi plus 0 is equal to the square root of pi dy dx minus 0 divided by the square root of pi squared, which is pi. Now, in fact, you could reduce that. We could just write this as dy dx divided by the square root of pi. And now the thing that we want to do is we want to solve for this dy dx. Well, let's just go to the next page and continue this calculation. So we have -1 quantity squared, but of course that's just going to be +1. So we're going to have 1 times 2 square roots of pi is equal to, and it's dy dx divided by the square root of pi. So now we can just multiply by square root of pi on both sides, and that will give us dy dx. So, of course, the square root of pi times the square root of pi is pi. So 2 pi is equal to dy dx. So the slope is dy dx equals 2 pi. Now this is the slope of the tangent line at the point square root of pi comma 0. So if we just rearrange this, there we go. The slope of the tangent line at this point is given by dy dx equals 2 pi. And that's what we were asked to compute. And now we've done it. So even though we started with a very complicated equation, and when we computed the derivative of both sides of that equation using implicit differentiation, we again ended up with something very complicated. But since we were just looking at this one specific point, we were able to just plug in x equals the square root of pi and y equals 0, and that simplified our computations quite a bit. And then we just solved for the unknown quantity, dy dx. Let's do another example. The curve having equation x squared plus y squared minus 2x quantity squared equals x squared plus y squared does not represent a function of x. Again, as you can see, depending on where you draw your vertical line, it might intersect 4 times. 1, 2, 3, 4. So this definitely is not the graph of a function, but again, we can use the same technique to find the slope of a tangent line. So we're asked to find the slope of the tangent line to this curve at the specified point. So once again, this point is given to us, and that will make our computations a little bit easier. So we start by computing the derivative of both sides. So we're going to have x squared plus y squared minus 2x, quantity squared, equals the derivative with respect to x of x squared plus y squared. Now on the left, we have something squared. So that's going to give us 2 times that thing times the derivative of whatever that thing is. X squared plus y squared minus 2x. That's just the chain rule. Our inside function is x squared plus y squared minus 2x. So it's something raised to the 2, so you use the power rule and it becomes 2 times that thing times the derivative of that thing. And on the right side, we have the usual kind of sum of x squared and y squared. So the derivative of x squared is 2x, plus the derivative of y squared is 2y times the derivative of y. And again, remember, we're using the chain rule here. It's something squared, so our inside function is y. So you compute the derivative of that thing squared, and you'll have 2 times that thing, but then you have to multiply by the derivative of that thing. It's just the chain rule, and in fact it's very similar to the chain rule that we did on the other side. It's just a little bit simpler because it's just y. Now we also need to compute this derivative right here, so that's going to be 2x plus, and now we've encountered a y squared again, so that'll be 2y dy dx minus the derivative of 2x is just 2. So now we have 2 times x squared plus y squared minus 2x times 2x plus 2y dy dx minus 2, and all of this is equal to 2x plus 2y dy dx. And again, we could just solve for dy dx and get a general formula, but we're given a specific point, and so now we can just plug in x equals 1 and y equals the square root of 3, and that will make our computations a lot simpler. So at 1 comma square root of 3, again, x is equal to 1, y is equal to the square root of 3, we can just plug that in. We'll have 2 times 1 squared plus the square root of 3 squared minus 2 times 1 times 2 times 1 plus 2 square roots of 3 dy dx minus 2, that's supposed to be a 2, minus 2 is equal to 2 times x, which is 1, plus 2 times y, which is the square root of 3, dy dx. And now we can simplify this and again solve for dy dx. So let's just go ahead and do that. So we have 2 times 1 plus 3 minus 2 times 2 times 1 is 2 plus 2 square roots of 3 times dy dx minus 2 is equal to 2 times 1 is 2 plus 2 square roots of 3 times dy dx. So again, we're just trying to solve for dy dx. So we can simplify this a bit. This term, 1 plus 3 is 4 minus 2 is 2. And here, the 2's will cancel. So this 2 will cancel with that 2, and you're just left with 2 square roots of 3 dy dx. So we've got 2 times 2 times 2 square roots of 3 dy dx is equal to 2 plus 2 square roots of 3 dy dx. On the left, we have 2 times 2 times 2 is 8 square roots of 3 dy dx. And on the right, we have 2 plus 2 square roots of 3 dy dx. And again, we're just solving for dy dx. So we get them all on the same side, so we'll have 8 square roots of 3 dy dx minus 2 square roots of 3 dy dx is equal to 2. We factor out the dy dx, and we'll have dy dx times, well, 8 square roots of 3 minus 2 square roots of 3 is 6 square roots of 3. That's going to equal 2, so dy dx is equal to 2 divided by 6 square roots of 3. This reduces to 1 over 3 square roots of 3. So the slope of our tangent line at this point is 1 over 3 square roots of 3. And that's our answer.